talked about constraints and inequalities, but there's one more bit of terminology that we need to figure out a linear programming problem. We'll call any combination of values for x and y that satisfies the constraints a feasible point. We'll call it a point because, as you'll see, we'll be representing it geometrically. If we collect all the feasible points that there are, we'll have what's called the feasible set. Now we can restate the problem we started with in true linear programming terms. We want to pick from this feasible set the point that has the highest profit. Stating the problem clearly, mathematicians always say, is half the battle. On the other hand, it's only half. Right now we know the rules, but we still don't know how to find the optimal solution. In other words, we could pick the optimal feasible point from the feasible set if we only knew what the feasible set was.
Let's create a map to search for our feasible set. You may recognize it from your high school days. It's called a Cartesian plane. We'll label the horizontal axis x to represent our unknown number of cranapple gallons, and we'll label the vertical axis y for our unknown quantity of appleberry juice.
Plotting our constraints will be the first order of this side of the juice business. Remember, our supply of the ingredient cranberry juice is limited to 200 quarts, and we'll need 3 quarts of cranberry for every gallon we make of cranapple, what we've called X. We also need 2 quarts of cranberry to satisfy our 1-gallon appleberry recipe, which we've called Y.
Now we're ready to plot our inequality. 3x plus 2y is less than or equal to 200 by drawing a line that separates the plane in two. On this side of the line, the points call for more cranberry juice than we have. All these points call for less than the 200 quarts we have, which means this yellow region represents the amounts of cranapple and appleberry that can be made without requiring more cranberry juice than we have. The points that fall directly on this straight line, though, call for using exactly the amount of cranberry we have available. These are the points where instead of having an inequality, we can use the equal sign. So we can label this line as 3x plus 2y equals 200. It's a familiar expression, but we've replaced the inequality sign with an equal sign, making it a linear equation. This line, then, the divider, indicates the points where there's exactly enough cranberry juice to carry out the maximum profit policy.
I've basically been dealing with one constraint, the principle that we couldn't use more cranberry juice than we had available. But there's also a constraint on the amount of apple juice available.
If we repeat the steps I went through with the Cartesian plane, we get a graph like this. Again, we have regions which require more apple juice than we own, and regions where apple juice would be left over. The boundary line represents using exactly the 100 quart supply of apple juice we have. In this case, the equation for the line is x plus 2y equals 100. Keeping our recipes in mind, this equation represents that we need to include 1 quart of apple to make 1 gallon of cranapple juice, or X, and we need 2 quarts of apple to make 1 gallon of appleberry juice, or Y.
We figured out some important information about each of the pieces. What happens when we put it all together? We want to apply all the constraints at once. The fact that we can't use more cranberry juice than we have, the fact that we can't use more apple juice than we have, and the fact that we can't make any negative quantities. Well, that amounts to putting both of the lines that I developed separately onto the same picture, the same coordinate system, and seeing where the feasible regions overlap.
You can see that the lines have now divided the positive part of the plane into 4 areas. This upper region includes points which aren't feasible because you wouldn't have enough of either kind of juice. In this wedge, we'd have enough cranberry juice, but not enough apple juice. The reverse is true down in this wedge. Here, between these lines, we're talking about having enough of both juices. Now, if we zoom in a bit on the feasible region, we can identify 4 corner points. What's more, we can label each of them with their Cartesian coordinates. 2 of these 4 points have coordinates that we had to compute in order to draw the line in the first place. Our third point is labeled 0, 0, and we know that because it's at the cross point of the axes. But figuring the coordinates of the 4th point again entails a bit of algebra. The technique in a nutshell is to take the equations for the 2 lines and solve them simultaneously. I don't want to veer off on that, so I'll just give you the results. Voila! the feasible region we've been after. But there is one drawback. This region contains an infinite number of feasible points.
Now you can decide without any prompting from me that some of these points may not represent such great production policies. The point 00, for example, doesn't sound like it's going to make much money because it's not going to make any juice. But we're still confronted with a lot of possibilities. In fact, although we seem to be closer to a solution, there is still an infinite number of feasible points in our diagram. An important discovery about linear programming problems is that there is a principle that can help us narrow our search, the corner principle. This principle says that the best profit will be at some corner. In this case, we only have 4 corners, so the answer should be in striking distance. The way we proceed now is to take our profit formula and compute the profit for each corner by plugging in the numbers one at a time.
That formula, remember, was profit equals 3x plus 4y. We've already eliminated the 00 corner. As I step through the other corners, we can store the results of each profit calculation next to the corner coordinates. From the calculations, we see that 250 is the highest profit, and it occurs at precisely this point. And thanks to the corner principle, I don't have to test any other points, whether they're on the lines or in the yellow region. The corner coordinates are the only ones that are in competition.
The corner principle is pretty powerful, but I don't want to leave you thinking that it's magical, just pulled somehow out of a hat. It's a consequence of our profit formula, 3x plus 4y, or rather I should say, of the kind of linear equation that our profit formula represents.
On the graph, I've drawn a line that represents an arbitrary profit of 150. It crosses the feasible region, so all the points on it represent production policies that we could carry out. But clearly, this is not the maximum possible profit. I'll let the profit line inch up the graph. Each time the line moves, the profit it represents is also inching up, from 150 to 151, 152, and so on. If the line moves so far up that it no longer touches the feasible region, then the value it represents is no good. Now, the corner principle simply observes that at the instant when you're just about to kiss the feasible region goodbye, you must be touching that region at one point at least, that is, at one corner point.
Let's not lose sight of the fact that we got our answer. The coordinates of that best corner, 5025, give us the production policy that yields the highest profit. So turning a real-world problem into a set of linear equations requires a thorough understanding of the ideas we started with: production policy, constraints, and optimization. And plugging our mathematics back into reality, we find that the optimal solution to our juicy problem is this. Our production policy should be to make 50 gallons of cranapple and 25 gallons of appleberry for a total profit of $2.50.